Hello there, my name's Andrew Prentice. I'm a member of the science faculty at Monash University in Melbourne, just south of Sydney. So for many years I've been interested in the formation of the solar system and how the planetary system formed. And just in recent times my interest has dwelled on Pluto and Charon and of course Arrokoth a little further out. So the whole solar system looks like this. It's basically a flattened structure with all the planets in nearly circular orbits, except for Pluto and Charon, which is an inclined orbit, but that may have come about as a result of a collision. It's something we won't worry about just at the moment. But the rest of the solar system has a lot of regularity, suggesting it may have formed from a common cloud. And that will lead us to the ideas of Laplace, that the whole solar system formed out of a great spinning cloud. Now let's look at the Pluto-Charon binary in its physical and orbital data. As I mentioned earlier, it orbits out there beyond the orbit of Neptune. But if you look at it's really a binary, and if you look at the ratio of the masses of Pluto to Charon, it's 8:1. And that's exactly the mass that Raymond Lyttleton predicted if Pluto and Charon had once been a single rotating body of liquid that fissioned into two parts. The ratio of the masses of the two parts would be 8:1. The other extraordinary thing which has come about through New Horizons and also studying the orbital dynamics is that the angular momentum density of the system, if you store all the angular momentum, spin and orbital together into a single body, then this coefficient, which is called big J, is equal to about 0.39. Now that coefficient coincides exactly within the error bar to what is expected if the Pluto-Charon system was once a single rotating fluid. I think it's been shown to be 0.3896. That's some work that was done by Jeans in the first part of the last century and other scientists as well. So there's a lot of data that supports the fact that the Pluto-Charon system formed through fission of a single rotating body. And maybe in the beginning Pluto and Charon looked a bit like, they might have looked a bit like how Mir is today. That has a period of about, I think, 4 hours. But anyway, they would have had that sort of structure. Now, so those are the facts. We've got the ratio of the 8:1, and we've also got the angular momentum density, all pointing to a fission origin. And if we go out to Arrokoth, that object, I think it may have started out as a single body, but if we look at where it is today, as I mentioned earlier, it's way out at about 44 astronomical units, sitting right more or less square in the middle of the cold classical Kuiper belt, very little eccentricity. It's as if it is one of the condensates that formed out there with a whole lot of them originally, as if they'd condensed from a gas ring at a very well defined position, orbital position with zero inclination. The important things today, which you bear in mind about Arrokoth, is it has a very smooth surface, very few craters. It's got a slow spin period. The other thing, it's got a uniform dense color, very uniform red color, deep red, and it's also got a lot of methanol. We were expecting water ice, but instead of that, lo and behold, we've found this object, methanol. How do we explain those facts and the great differences between the Pluto-Charon system and Arrokoth if they'd started out? Well, my hypothesis is that both systems started out originally at 44 astronomical units, and both objects had the same initial chemical composition, and that chemical composition was about 22% of frozen CO2 ice and 5% of methane ice, but there was also admixed with rock, and in that rock there were a lot of short-lived radioactive nuclides like aluminium-27, which would have burnt furiously. And the first thing that would happen, it would have heated the object up from the original cold condensation temperature of way down to 26 degrees. It would have soon got up to 90 degrees, and at that point, the methane ice, it first melts, and then a little later, it vaporizes, and those vapors would rise up through passageways and in the unsettled surface of the original object, rise to the top, and then refreeze, and I believe form a solid cap. So you'd have an outer cap of frozen methane. And in about 60,000 years, it'll be getting warm enough up to about the 180 mark where the CO2 ice, in the case of Pluto, it's such a dense object that the CO2 passes directly into liquid. It's way above the triple point pressure of 5 atmospheres. And so that forms a great liquid. And a little later on, you get up to the 270 mark, the water ice melts. And so in the beginning, the Proto-Pluto system would have been had a vast liquid interior, slowly melting with lots of imprisoned rock, which makes up about 50%. And then a great spinning very rapidly. Not fissioning yet, but spinning rapidly, maybe the period of 5 or 6 hours. Then you come to Arrokoth. Unfortunately, it's so small, the pressures are way down at about 0.4 of a bar. There's no way that you'll get melt. The CO2, after the methane had initially melted and vaporized, as in the case of Proto-Pluto at 90, that would have gone up to form a cap on Arrokoth. But the CO2 ice, it goes directly into vapor. And those vapors rise up, tracing up behind where those methane molecules had gone. But when they get to the top, unfortunately, the methane had formed a cap around it. Meanwhile, the furnace is burning furiously below, aluminium-26 burning, and more CO2 comes up. And then I predicted about late 2018, November, that the whole surface would have been broken apart and disrupted because the buildup of pressure would have caused an explosion, and that I predicted the original surface of Arrokoth would have been smooth and crater-free because of this process. And so we have this idea that this early composition would lead to 2 different paths, one for Pluto, forming a great liquid interior, and one for Arrokoth with all these explosive vapors. Now, is there a way of putting this all together? There, by the way, is my picture of the early single Arrokoth object as a rough spheroid imprisoned with all these ices. And then had a very rapid period of 5 to 6 hours, and then it split apart because it was rotating so rapidly, it's irregular, and centrifugal force would have caused the thing to rupture. And the favored plane is the equatorial plane. It would split the 2 lobes, and then hopefully they'd refreeze before they drifted off into space. And that will in fact lead to a period of about 16 hours, starting off with 5 to 6. For the Pluto-Charon system, as I said earlier, you've got a vast liquid interior, not enough for it to fission, but it's all imprisoned with rock as well. Now, a very interesting thing happens now, and this is a key point. The rock particles feel the effects of gravity, and they start to co-settle towards the center of the object to form a giant core. And as they settle, the object starts to speed up, particularly if the ice hasn't sort of fully melted, the rock's drifting, and that is the trigger for fission. As soon as I reckon about 50% of the rock had got to the center, the object sped up to the point where, according to Littleton's work, the object would pass from a triaxial ellipsoid to a pear-shaped structure. It would fission. 1/8 of the mass would go off into space to form Charon, and that object, a great globe of liquid, would be deprived of rock, the rock that had already settled to the center. So Charon is expected to have a lower density than Pluto. Pluto would then make do with what was left behind in the great globe, and it would have a higher rock fraction. And so those are the 2 primary ideas, one for Pluto-Charon and one for Arrokoth. Let us now quantify this whole process, and I use the Laplace model for all my calculations. For 50 years since I left Oxford, I've been trying to, thanks to my PhD mentor Dirk Tahar in Oxford, he suggested I reawaken Laplace's idea with theories of turbulence that he himself had worked on many years earlier. And he thought that this might provide a clue to how Laplace's theory would work. Of course, others had looked at Laplace's model and it had been rejected. The primary reason is the masses of the planets all put together is only 1,000th of the mass of the Sun. And if Laplace's ideas were correct and the primitive Sun had become rotating sufficiently rapidly that out of the orbit of Neptune it had become rotationally unstable and shed its first gas ring, then in order for that cloud to contract through to the present-day Sun, which is spinning so slowly, it would have to give up all of its mass. But in fact, we know the Sun commands the bulk of the mass. And that mass-angular momentum dichotomy led to the Laplace's model being abandoned. Tahar, who I mentioned earlier, suggests I include turbulence into the model. And if you include buoyant-driven turbulence through gravitational, through thermal convection, and then gravity, of course, the idea is that the buoyant convection depends on the distance from the center. It's driven by mass. Buoyancy forces are much stronger in the outer layers of the gas. And these outer regions, if there is a turbulent stress arising from very strong convective motions, that will have a greater effect in the outer layer. The outer tenuous layers are pushed outwards to a great distance, and the globe would become very centrally condensed, and you might achieve the point that Sir James Jeans had mentioned back in the 1920s. That Laplace's theory could be restored if the primitive Sun had been very centrally condensed. And lo and behold, the inclusion of supersonic turbulence does cause that to happen. So the moment of inertia gets very small. There's a great density inversion at the edge as the turbulent stresses die away. The cloud, if you include rotation, it has a shell around it, a very dense shell, non-turbulent gas, and as the cloud contracts inwards, it speeds up and that shell slips down to form a belt. And because of the turbulence, there's so much mass stored at the end that instead of just throwing off mass continuously, it actually throws it off in gas, in the form of gas rings. And here we can see the cloud contracting inwards and shedding, looking at it side on, has a lenticular shape, and it sheds first the ring at Neptune's orbit and then at the orbit of Uranus and so on, and until it gets to the present stage. And so the primitive solar system would have had this nested set of gas rings. The nice thing about them is that gas rings are geometrically spaced because of homologous contraction. You can account for Bode's law, a very low moment of inertia there, F, to explain the masses. And the gas rings, very nice properties. The gains settle down to form a concentrated stream, and that allows the process of accretion to occur. I've done a more advanced study there. I've done another study with a former PhD student to show that you actually do get supersonic turbulence. You don't actually get quite up to supersonic. You get to supersonic speeds, transonic, but not supersonic. And as a result, you do find this steep temperature inversion and at least density inversion. The temperature steepens up at the edge. And you do find a possibility of Laplace's theory can be restored. You find the temperatures vary as 1 over r. You can compute the temperatures. I find that T goes as 1 over r. You can use mercury as a calibrator to find the temperature of the Mercurian gas ring, about 1600. And knowing that, you can go out to the orbit of the cold classical Kuiper belt, work out its temperature formation at 26 degrees. You can work out what it's made of, the condensates, and then the remarkable thing is you've got that 22% CO2 ice, you've got the methane ice, which I mentioned earlier, and this very proportion of things come out naturally out of the model. You can then look at that, go back and look at the fission model, and I mentioned how the formation of the fission of Pluto occurred. The triggering of the event was the settling of the rock to form the center. 52% gets to the center, and when it fissions, the globe that goes out to form Charon is rock deprived. You can actually use that, knowing the density from New Horizons of Charon is 1.702, you can compute that rock fraction exactly that's inside Charon, about 0.411, and you pin that down, that's the settled rock fraction. You then go back and you get this very nice model there for Charon. You then go back and look at Pluto. You know how much rock's in it. You evolve it for 4.56 billion years. And lo and behold, if you work out its density from that model, knowing that it has 55% rock, you get a density of 1.86, which coincides with the New Horizon value. It's all come out of this compositional model. And that's a very nice outcome for so many years of work. I've worked on all the planets from Mercury, the iron planet, out through the Jupiter system, Galilean, Saturn, and I've come right to the very end. And the whole model is self-consistent, and I welcome anyone to go over my calculations and look for anything that might be incorrect. And finally we come to little Arrokoth, who's been waiting this long for us to be seen by New Horizons. I believe it started off as a single body through sublimation of CO2. It split apart. It was once a single globe. It split into two parts. The amount of methane ice that vaporized was about 60%, CO2 30, and water only 1. That led to this structure that we see today, this rotating, this flattened object, because the two halves, the upper and lower hemisphere, split apart. It was probably slightly irregular. They slipped apart, and fortunately, they just, before they escaped into space, the ices must have refrozen, and they just stuck together, and we just caught them as they are today with that flattened period. So that's the story. The model I had ahead of time predicted that Arrokoth would be smooth and crater-free. There are a few craters, that is true. It does seem to have an outer shell. It could be something like 400 meters deep of pure methane. Very little water ice, because there's very little that came up. What little did come up reacted with the methane through radiolysis to produce the methanol, and I believe this model successfully explains what we see today. Thank you very much, COSPA, for giving me the opportunity to speak to this assembly. Thank you.